Cochran, he's a cell biologist whose research examines the impact of impaired cholesterol, hemostasis, and cellular function and related complication in cardiovascular disease and diabetes. His research has grown to utilize 3D printing approaches to answer questions in physiology and anatomy. He's also developing 3D printing-based pipeline to examine the impact of cellular function due to altering morphology and blood flow that occur in, I can't tell the last one.
Atherosclerosis.
Yeah, that's what he said. So let's listen to it.
Thanks everyone. Thanks to the organisers for having me here to speak. That's a really hard talk to follow. But that was amazing. So I'm just going to talk to you a little bit about some of the work that I've been doing. I'm just going to put my timer on because I'm one of those people who has no idea of how long I speak for, and I'm conscious of the fact that I'm the last person in the seminar. So, as I was introduced, my background's in cell biology. I kind of have gotten into 3D printing as a bit of an accident. I've tried to kind of combine the two together. I won't talk about that project today. I'm just going to talk about one thing specifically. I was talking to some of the people outside, the guys working for the 3D printing companies, and they have similar backgrounds. So I will apologise in advance when we go to panel. If you ask me physics questions, I won't know. I know some clinical stuff. I basically started working with medical imaging people to have a look at this really interesting mouse model that we developed and to get an idea of what was going on inside the mice. And being at a relatively big university with good infrastructure and all that kind of stuff, we've got a 7.4 Tesla MRI in the basement that you can stick mice in and take really beautiful pictures. And this was to look at a mouse model that we developed where we wanted to look at how much adiposity was subcutaneous versus visceral, and the amount of muscle in the mice. And so we used MR to look at this and then build applications around that to actually quantify it. And we also did some work with the University of Sydney looking at PET CT. And so this is the CT image of FDG uptake in a mouse a couple of seconds after it's been injected. So it's a tau vein going into the heart. And we use this to quantify uptake of the radio tracer into the actual muscle, which is all well and good, not so 3D printery, but that's how I got there. I've got two main 3D printing themes, and I think that this slide is actually now out of date after listening to Tim's talk a couple of minutes ago. So I'm going to talk to you about the thing that's going to show up next, is that, and I do this work together with Tracy Barber, who's here, about printing patient-specific coronary artery images. So we get these images from patients at Prince of Wales Hospital in Sydney. You can see the lumen, or the volume on the inside. It's quite simple. All my printing at the moment is just done on an FDM machine. I started on a $500 Aldi machine. I now use a $1,500 flash forward, so nothing overly fancy, nothing super commercial. And if you take people who have atherosclerosis, you actually end up with a stenosis in the wall of the vessel and occluded blood flow. And so what we actually do is we take these models and then we mold them in PDMS to have a material that has similar elasticity properties to the vessels in real life. And we're also able to coat the PDMS in proteins, fibronectin, and things like that cells like to grow to, and we coat them in endothelial cells, and we're basically trying to mimic ex vivo what goes in a patient's coronary or carotid. So carotid because it's a bit bigger, we'd like to get to coronaries one day. Also, we can use these models to test for 4DMR, and we can put these into an MRI, image them under constant flow conditions, under pulsatile flow conditions, and eventually be able to marry that up with the stuff that Tracy does on computational fluid dynamics to actually determine if our models are real, and then examine what the effects of, say, shear stress, wall shear stress on areas of stenosis versus normal areas and areas of perturbed flow. This has a really big function in atherosclerosis. Athero happens at bifurcations more commonly than in normal areas of vessels, and also in areas, once you start getting a plaque, the shape and morphology of that plaque likely contributes to the growth of that plaque. It grows at more at the edges of the plaque than in the middle, and that's due to wall shear stress changes and perturbed flow. And so we will be testing this with 4D MRI, and as I mentioned, we can grow endothelial cells on the cell. And so this is something that I'm not going to talk about any further today. It's all still work in progress. I'm going to talk to you about bone phantoms, and this is the absolute definition of beer science. So working with a guy called Will Ryder, who has a background in imaging, medical imaging. He now works for the Health and Education Training Institute in Sydney, which is run by the New South Wales government. They train all the radiologists. We were doing the images that I showed you earlier, and we went for a pint or two after work a couple of times and just started talking about what he was doing. And so Will's got clinical training as a clinical medical physicist, and he'd actually printed a full skull phantom in ABS that they'd sealed up, filled with so it was printed in ABS. It was anatomically correct based on images and acquisitions that he'd acquired himself. It was filled with doped water. I don't know what he doped it with. I think it was a radio labeled something. He wouldn't tell me. And for use as an MR Phantom. They started doing a lot of testing on this, and they covered it in plasticky dip, and it was awesome. And then someone dropped it on the floor at the hospital. And Will was also the radiation safety officer at that hospital. So after I think he calmed down, he was very sad. And this was actually just before the full characterization of this model was completed. So whilst he's presented it, he hasn't been able to finish it and write it up. And he was very sad. And once he calmed down, which took a long time, he said, right, we need to print something else. But he'd moved institutes, he'd moved house, his printer was in parts, it had stopped working. So we went, right, let's redesign. If you got to do it all again, what would you do from scratch? And whilst the ABS was really good for MR, we thought, why don't we have a go at CT? And having something we can use for both MR and CT. And so what we wanted to do was make a bone phantom, something that looks like bone, that is easy to print, that is cheap, that is customizable, and that somebody who isn't an engineer like me can actually print. And so there was a couple of questions. Should we use PLA? Should we use ABS? You know, everyone has their own preferences. I personally like PLA because you don't have to heat the chamber up. It doesn't smell. Your lab mates don't complain about it stinking. You know, it doesn't warp. It doesn't crack. All that kind of stuff. What should we include in the mix? What do we add in? What do we add that absorbs X-rays that will actually give us something similar to bone? You know, there are things on the market that are plastic merged with iron, with carbon fibre. You can basically chuck anything you want in there, but is that actually going to give you an attenuation similar to bone? And, you know, being a practical biologist and not thinking at all about materials, all about physics, well, bone's made of calcium, among other things. Why don't we chuck calcium in there? And so Will did an attenuation prediction based on the attenuation of bone, of PLA, and of water. And he estimated that if you were to mix calcium, this was based on, I think, a 30% mixture of calcium and PLA, you'd actually have attenuation somewhat similar to bone. You know, being practical again, the first thing that Will did was he came to the lab one day with a container of bone meal, so just ground up cow bone, and said, mix this, and that failed spectacularly. But we had to go start somewhere, so then we actually went and bought some nice, better calcium and worked with that. We had no money to do it. We had very little limited expertise. I didn't give it to one of my students because I'd have a student in complaining about their project not working, so I got stuck into it over a couple of weekends. And what we did is we took PLA. ABS would be cool because you can dissolve ABS in acetone for those who know about smoothing. PLA does not dissolve in acetone, so you've got to be a bit more, a bit crazier about it. And fortunately I work in a lab. You search the internet, they're like, oh, not much degrades PLA. People on forums don't usually have access to chloroform, which is probably a good thing, but we do in the lab. So I mix this up with chloroform, you end up with a sludge. It's really cold because it evaporates so fast. Dumped a whole bunch of calcium in there. Calcium doesn't dissolve in it, so you basically got to keep stirring this slurry because the calcium keeps on dropping down to the bottom. If you do this for long enough, you eventually can allow the chloroform to evaporate, and you get one thing, you get them kind of stuck together, not well. And if we show you a picture, this is what it looks like. So this is cheap, nasty PLA cut into pieces, mixed with in chloroform with calcium. You can kind of see the calcium is at the top and the bottom. It doesn't really mix that well. If you shred it up fine enough, you end up with something that you can put into an extruder. Now, who's you tried to use an extruder before? Well, a word of advice, yeah, up the back. Then the ones you can get, you know, buy your own material, recycle everything you use and use it. Look, getting a good spool of filament out of an extruder is not easy. You might get a meter or two that is kind of what you want. It takes a lot of fiddling around. And these are two models. So this one, this is a Filament. It's pretty good. We have one at the university, and then the recycling guys upstairs decided to take it out of the makerspace, and then I'm not allowed to use it, and then they broke it. And so that got too hard. So I went online and I bought one of these, which is a fill extruder, and I could make about 1 or 2 meters of filament at a time of the right diameter. Getting it consistent is terrible. But, you know, we're trying to do what we can. This is science. So I managed to make a composite. And what we found was that we were actually able to produce, this is normal PLA here and here, just on the printer. And we were actually able to print with about 1 meter or 2 of filament that was a reasonable quality discs. And we could test these. So we chucked these in the DEXA, so dual energy X-rays, and we can see that there's definitely high X-ray absorption or attenuation in the ones that contain calcium. And if we do CT, we get basically the same thing. Now, what I'm not showing you on this picture, these are nice pictures. This is what you put into conference proceedings, but this is nice, good plastic that's reliable. This is my 1 meter that was good, and by the time I got to the end of that 1 meter, it was pretty crummy. It wasn't 1.75 mils in diameter anymore. It was maybe 1.4. Kind of had to sit there, feed it through the machine. It's not the greatest quality print. Down here's okay, up here, rubbish. So with that in mind, I was able to actually take that preliminary data and apply for a grant through the Global Connections Fund. It was funded to go and visit these guys, Protopasta, and they are a filament making company. They're in the US. They're based in Washington State, just across the border from Portland. They're materials experts. They make weird stuff. They mix all kinds of metals into their plastic, and they've actually got materials background, and they've worked for Nike. So they've had an interest in making this before. I sent them an email and said, I want to make this. And they got back, yeah, we've had heaps of interest. It's great. Nothing. And I'm sure they get people kicking the tires all the time. So then I basically said, guys, I've got money. I'm going to be in town for these 3 days. Tell me if I can come in. And they went, all right, come in and we'll make it. And this is one of our schools of filament. They've got a really cool, flexible manufacturing process where they can make stuff. What was really important is they took the plastic, their special proprietary plastic, mixed calcium in together, and they've got this big giant tank of a machine that mixes them together by dual extrusion, no chloroform, no nothing. Originally thought the material was crap because it printed like this, and this is bad. What we found is if you take the really nice fancy tooth gear that they use for precision and replace it back with a really nasty gear, it actually prints much better. And these guys, being from Washington State, printed a beaver skull, which was kind of cool. And I saw it online. They didn't realise I followed that account. And I went, hey, the beaver skull looks cool. Is that my material? And they went, oh, yeah, it is. So we've actually gone ahead and we've printed it ourselves. This is Gary. This is Catherine Broadhouse. So she's a medical radiation physicist at Sunshine Coast. And so Gary's twin's actually outside. His name's Peter. It's the same Thingiverse file, I swear. So Gary actually has a brain. Gary's brain is full of something resembling agarose, and his eyes are full of agarose as well. Gary on a CT machine looks exactly like you would expect. I really hope my video loads. Yep, he looks just like you and I on a CT. And this actually, when we look at the Hounsfield units, has a value very similar to bone. There's some slight regional differences, but we'll take that for now. You can also print smaller things as well. So this is the top of a humerus. It looks really good on the outside. It's not actually anatomically perfect on the inside. However, this metacarpal actually has all the right gaps and everything on the inside because it's from a CT. And so if I show you this, you can actually see This is based on a CT of the metacarpal that it actually looks like what we want, and for those of you even more medically inclined, you can actually see it's got all the gaps and everything on the inside. You've got to make sure you turn the support material off before you print, because otherwise you end up with zigzags inside your prints. And that's just to convince you again that when we put these on a CT, it looks exactly like, or basically similar to what we would see for a finger. And what we're going to use these for is to do for medical training. So the anatomy guys at the university, this costs, you know, a couple, not even dollars to print these things. If you take one home, if a student puts one in their pocket, you haven't got to worry about the ethics around it, all that kind of stuff. If you break it, you can print another one. And also, you know, the flexibility around surgical planning as well. So we're hoping to actually, I think they're going to start selling this stuff pretty soon. It won't be that particularly expensive. And I'd just like to acknowledge the help from all the people that are involved in this, and for ATSC for the funding that made it happen. So thank you very much for listening.